Thanks, Laurent. Thanks to all the HNR community to having me here. It's a great pleasure and honor to close this event. In this presentation, I propose we distinguish between 3 different ways to integrate geographical places in network analysis. First, it's when you have information on direct links between individuals, organizations, firms, and you aggregate them at a geographical level. Second, it's when you have indirect information on the presence or absence of entities in a geographical place, and you use them to infer a relation. And third, it's when your information is spatial from the beginning, and so you have direct links between spatial entities. So I'm going to give you some examples of these different types of network, and then I will take up the methodological proposals of collaborative research we've done on the visualization of scholarly worlds from Antiquity to the present days. So to begin with the first type of network, most researchers are studying this type of networks, considering geographical places just as classic attributes. And I argue here that geographical places can be also relevant aggregation levels to study this type of networks, because they can help you to better understand the underlying structure of these networks. But of course, aggregation always comes at the price of losing the internal variations. And nevertheless, it's often a very heuristic step to make. But to do so, however, you will need to choose a relevant geographical unit, which can be a perimeter or a grid on a spatial regular grid. And you will have to choose also a normalization method to weight the links between the places. I will come back to that later. Just to begin, I give you an example among the different types of direct relations that you can consider. I give you an example of personal network analysis derived from a longitudinal panel survey. In personal network analysis research, there are 2 common indicators that are traditionally considered. The geographical homophily between the individuals that are studied. That is to say, the tendency to relate to people that share the same place as you are. And also what the researchers, often sociologists, are looking for is the geographical distance between the network's members. So it's only at the inter-individual scale. And what we are proposing with 2 sociologists, Claire Bidard and Gilles Viry, is to think about what we could learn from this type of data sets, so personal networks data sets, by analyzing and mapping them at a spatial level. So we are trying to develop a common methodology that can be applied to different surveys. I'm just going to give you the example of what we get with the survey from Claire Bidard on the Caen panel. So we have decided to use the EGO network that she has from the Caen survey. And we use the networks and we aggregate them at the employment area level. The employment area level is a statistical perimeter that makes more sense, according to us, than the municipality level, since the delineation is not purely administrative, but it's based on commuting data. So here it's what it looks like in the case of Jean's personal network. So here it is Jean, a map of personal relationships when he is in high school in Caen. And here it's when he's back to his parents in Caen after graduating in Le Mans, so the other, the second node in terms of size, since the size here is proportional to the number of alters in Jean's network. And here it's when Jean lives in Rodez with his partner, and they have just changed their job. And here it's when they are back to Caen together, and again they change their jobs. And to finish, in the last wave of the survey, Jean is still in Caen, but now he's divorced and again has changed his job. So it was just an example of the fact of the interest of doing this to analyze this type of networks that are, because it gives you an idea that without doing this, Jean would not have been for us as much interesting, because it's when we have done that that we have realized it was a very uncommon individual, since his spatial networks really evolve at each wave of the survey. So let's go to type B networks now. So type B networks is when you have to infer the relationships. It's indirect. And there is two types of co-presence networks. Sometimes you infer the relationships between the species or individuals. It's often used in ecology or biogeography. That's why I speak of species here. And so you infer a relationship because they share the same place. And in this case, it's what Zachary Neal called location as artifact in this type of networks. And the other situation is when you infer a relationships between the places share certain characteristics. And so because the information on the links in these types of networks is indirect, there are many ways of controlling the information, normalizing the information, to make sure you will only keep the most significant relation. So in the literature, in biogeography, there are many ways of trying to be sure that if you simulate the same situation but at random, then if you compare with your actual network, the links that you observe in your actual networks are different than the one you have observed if the distribution was random. So there is a very vast literature on the topic, and different methodologies have been proposed. Some offered to simulate null matrices, others proposed to just compute probability of co-presence using the different distribution probabilities. Whatever the method that is used, there is always risks for type 1 errors and type 2 errors. This is the way they are called. So type 1 errors is when you have some relation that your method tells you that they are very significant, although they are not. And type 2 error is when, on the contrary, certain relations given your model are considered insignificant, although they should have been considered significant. Using this type of statistical approach can be useful to two different tasks, either to simplify your network, and so extracting backbones. There are many methodologies to extract backbones, but it's one of the ways to do this. And another possible application then is once you know which ties are the more significant, then you can compute the similarity or the similarity index to know which species maybe are similar, or if you are working on individuals or cities, which cities are similar, for instance. So here I give you a very canonical example in biogeography. It is the distribution of the finches in the Galapagos Island. So as they were first documented by Charles Darwin. So this data set is very common in biogeography, and you have 13 bird species distributed in 17 different islands. So here is the presence-absence matrix of this data set. And what Sanderson proposed in 2000, so here is the figures I've taken from this article. Sanderson was a computer scientist. He was not coming from the ecology before, but he was acquainted with this question and this data set, and he proposed a way to simulate all the possible null matrices, which according to him was not the case before in the literature. So he came up with a new methodology to do this. And so comparing the actual matrix with random matrices, he showed that some of the links were less often, some birds were less often together than we would have expected from if the situation was random. And it was doing this, actually what he finds was consistent with what we already knew at the time, that is that the birds with the biggest beak are not on the same islands because they actually are competing for the same foods. So they tend to be located in different islands. I can be more specific and give you more detail at the end if you'd like. Here is just to show you the other type of type B network, when what you want to infer is not the relation between individuals or species, but the relation between cities. And what you use to infer relation between cities, in this case, you can use this fact that they share common characteristics. And here it's also a classic example from Peter Taylor, a geographer, urban geographer, who consider that cities having the same bank group and the same producer service installed in this city are more similar than others. And for instance, New York, Tokyo, and sorry, I have the New York, Tokyo, and New York, Tokyo, and London, yes, are the only cities that have the 3 types of services present. And so you can also observe this here on the matrix. So on the rows are the cities, and the type of service are the columns, and so that's the way then he infers relationships. To finish with this type of network, I just show you an example from my own work with Maëlyn Strouk. So here we were just interested in the location of scientific stations in Arctic. And we decided first to map them. And so what the map shows is that most of the stations are domestically owned, but some of the stations are owned by foreign countries, and it looks like stations that are owned by foreign countries are concentrated in the same area, right? But actually it's not, we can't say much more with this map. And what I proposed was to look at this information more as a bipartite graph. Actually, it's a bipartite graph between places, but not in the same way. I mean that the blue square here are the places where the stations are located, and red circles are the affiliation countries of the stations. And so you immediately see here on this visualization that the archipelago at the north of Norway, so named the Svalbard, concentrates almost all the non-Arctic stations. And here it's clearly very complementary with the map, since we can immediately visualize this very specific distribution. And here you really don't know, don't need to do any kind of normalization or so on, because it's only like it's only one station per place. So there is no point in doing this, and you don't need to do it because you don't have so many links, right? So that was just an example of the fact that you just don't need always to normalize your data. and type C network. Now, I just give you an example again, similar to the previous one, is just to show you that when you look at, here is trade data, you can, of course, map them, which is an interesting move. But it's very also interesting to look at, so here is the waste data for waste, paper waste, and here it's e-waste. So of course, you can visualize the fact that you have two different distribution, but it's not so clear as it is when you just aggregate the data and look at just take the most important links between the countries. And so here for the paper, you immediately see that China is central. And for e-waste, you have a very different pattern, right? So now I'm going into the scholarly world. I just want to talk to you about an article we co-authored with two historians, Anthony Andurand, specialist of the Antiquity, and René Sigrist of the modern time and the chemists in modern time. So we have worked together on visualizing a scholarly world with different sources and methodologies. Our hypothesis was that scientific activity produces abundant documentary traces that are from different nature through time, and that it's possible to use these traces to reconstitute scholarly worlds and also mixing spatial approach and network analysis. So this is what we proposed in this paper with an interdisciplinary dialogue and in line with the current trends of digital humanities and science mapping. I just show you the example of the Plutarchic world and the contemporary world. I don't have time for the chemists, I'm sorry. So for Plutarch, what was done was studying the scholarly banquets that are described by Plutarch in his Table Talk book. And so doing so, Anthony Andurand find that information about 89 characters and 55 banquets, and then he looked at the place where the banquets happens and also the place where the different participants were from. And then he built a co-attendance networks. And what we have done together is to aggregate this information at the spatial level. So on the left, it's at the aggregation depends on the city where the participants are from. And here you can see that there is a big importance of Kéroné, which is the city Plutarch is from, and where he has many characters in relation with are also in Kéroné or from Kéroné. And then also what we have realized working on this network was the fact that he was really central. So if you remove Plutarch from the network, the relation with the Roman Empire are less strong. Now I'm going to talk to you about the Web of Science, contemporary science world. So what we have done is to look at a database which is very popular in scientometrics, since it encompasses a lot of scientific journals, and so it's very useful to look at the world science, let's say, although it has many bias. So we have used this information, and for each articles that are in this database, we have geolocalized all the addresses of the authors, and then aggregated them at the level of urban areas. So here is the network that we can get looking at co-authorship. So when different authors from different cities are co-authoring papers, and also the map of the 200 cities where they are the more who are involved in the more collaboration, the more important number of collaboration. So to do so, we have decided to delineate our own perimeters of aggregation, because the perimeter you have when you just geolocalize the data, so it's latitude and longitude, and it's usually at it gives us the municipality level. it would not be very good for comparing the cities at a world scale. So what we have done is that we have delineate perimeters that using the way density of population is spread. So it was a way to avoid the problem of administrative fragmentation from a territory to another. Doing the aggregation makes possible to compare Beijing, which is a very big municipality, with places like in Lyon, where you have a lot, agglomeration of Lyon, where you have a lot of different municipalities, and also Cape Town, where you have Stellenbosch University, which is different from Cape Town, but in the same conurbation, right? So doing the aggregation at a higher level, avoid to consider these different places as different, different, but to consider them as homogeneous different units that we are comparing. And so for the weighted projection method, what is interesting is that we have taken into account the bipartite information, the fact that some papers are signed from many cities at the same time, whereas some papers are signed from only 2 cities. And we have weighted the links according to the number of cities that were involved in one paper. So here is the details of this weighting method. And when we have then updated the information after the paper I talked to you about, we have done this work at several dates. And so here it was for 2007. You could already see just taking the more important links in terms of number of collaborations. So here you can see the importance of China already, but then we have updated this until 2030. So in the time of about 10 years, China is now as important as the United States in its participation in the world science, measured as it can be measured by this database. And another thing which is important to notice looking at this network is the fact that it's very nationally structured. Actually, it's not only certain big cities that are connected to the other, it's national systems that are really connected together and then involved in the world system. What you can do later on when you do this type of work is that you can again aggregate the data to have a better picture of the world scale and the world exchanges and their evolutions. If you want to know more about this work on geography of science, you can go to our website. It is frequently updated, and we are also trying to develop a tool that you can already use in beta version if you want to map bibliographic data that you extract from the Web of Science Scopus, or that you have yourself. If you have bibliographic data and the address of the authors, you can use Netcity to do this type of maps. Here is the scientific collaboration of the scientists that are working in Roscoff Marine Biology Station. And so with Netcity, you can do this type of map at the country level and also at the urban area level using our perimeters. To conclude, I think we could just try to remember some of the ideas I have developed during all these different examples that I have shown. First is that so when you transform type A network into type C, it can be useful because the spatial level can help you to better understand the social level. So it's the case in the example I have given to you about scholarly worlds. You can also think about the relation between type A and C the other way around, thinking about the fact that doing so can also help you to answer geographical questions, like pure geographical questions, like for instance, social data could help you to better delineate functional urban agglomerations. Social data could also help you to better model epidemic spreading at the geographical level, or to think about globalization. I would say that for the geography of science work that we have done, it's both doing the geographical aggregation both help us to better understand how the scholarly world works socially, and also it helps us to better understand how the world system is working more geographically speaking, like taking into account the globalization and the international relationships and so on. So then you have to keep in mind that transforming A or B networks into type C, then there are many methodological issues to deal with, like the choice of a spatial aggregation level and the choice of a normalization method. And to finish, also, you could, it's important to remember that doing all this type of network analysis manipulation sometimes make us forget that it's not only dyadic relationships, and sometimes places are connected, like it's more like triads and so on. And so now there are in the field many ways of dealing with more complex patterns. And also what I want to insist on is the interest of working with many dimensions and scales. And this is what I wanted to insist on, looking at the geographical space, speaking about the geographical dimension, but we could also consider time as proposed by Claire Lemercier. Of course. You can find all the different references I used to make this presentation, and some data I used to make some apps and networks on a repository that the address is here. And then I just want, because I think it's relevant as well, to mention two research projects I'm involved in currently. One research project on the Congress's participants network in the contemporary world. So we are comparing two Congress, one in science politique and the other in green chemistry. And so we have a new website and Zoterobibliography. If you want to contribute to the Zoterobibliography, you can send me an email and you will be a member. I will be glad. And then also, I think it can be interesting to mention the work of colleagues. I'm working together with them, but I'm less involved in this project than in the first one, to develop an open and free web application to generate flow maps. And it's already online, so you can try it if you want to make your own flow maps. So then, and to finish, I want to big thanks to Laurent Boguit and Martin During for the organization, and Claire Lemercier. And thank you.